Perfect. So I've always been working with databases, a lot of traditional databases like DB2, Oracle, Postgres, using traditional B-trees. I've also been developer advocate for Yugabyte that uses RocksDB, LSM-Trees, and now I'm developer advocate for MongoDB that uses WiredTiger for the storage that has B-trees, but a modern version of B-trees. So the goal is to compare not only the main differences, but the different optimizations that were made on it. Because we can go fast and have only one slide and say LSM-tree is better to write, B-tree is better to read. First, it's not completely true. Both improve the two workloads. But also, there is no database where you only write, and there is no database where you only read. Usually, you put something in the database with the goal of querying it later. And even if you write, if you have a write-heavy workload on your database, when you write, you may read a lot also. For example, except if when you insert in a SQL database, the database must check if the key already exists, or raise an error if not. It has to read for that. Even if you upsert, you don't have to read. But if you have secondary indexes, you cannot just upsert them. You have to write something. And think about the MVCC visibility, think about checking if something is locked or not, checking the foreign keys. So finally, you may think that you have a write-heavy workload because you are ingesting a lot of data, but the database is doing a lot of reads behind that. Something that is sure in databases, you need sorted structures. You can write to a log, you can write to a heap table, but if you want to query some values, and then you need to get a structure to find those values. For point queries, the structure can use a hash or be sorted. For range queries, it must be sorted. So the data must be indexed because you query it, and it must be indexed with a sorted structure. And there is an additional constraint in most of databases. You have a lot of data, so this sorted structure, the index, cannot fit entirely in memory. We need a structure that has some optimization for some parts in memory, but also when it comes from disk. If I take an example of sorted data, so this data is sorted, each line is sorted. Think of it like blocks on disk, for example. They are not all sorted, but they are not overlapping, which is quite good. With this data, I can get it sorted quite easily if I know where to start. I just need a pointer to the block where I need to start. And if in addition to that, in each block, I have a pointer to the offset of the next block logically sorted, I can just follow the pointers and get something sorted. But this is a lot of pointers to follow. If it's on disk, this is a lot of latency. So to accelerate those search, we can put more metadata in memory to get faster to a specific value. For example, if I search for my name in that, I can pick a pointer, go to it, I see that it is after it, then I take another one that is later, it is before it, and with this dichotomy I can finally find my name with following less pointers just because I had a bit more information in memory. We can put even more in memory. We can put also not only some pointers but some values. For example, a skip list where I can read the list and see that everything that starts after F, I can skip directly to a pointer there and go directly to the block. So that's really effective, having a structure that is optimized in memory, like a skip list, and having a structure on disk where I don't have to follow too many offsets in the file, too many seeks in the files. And we can go further with a B-tree because the problem is at some point the metadata that you put in memory to be efficient, and if you have a lot of data, may not fit entirely in memory. So the idea of B-tree is to have multiple levels of metadata before going to the final block that holds your data. This is a B-tree where at the top I have root information with some value that will tell me where I can find more detailed information about the ranges. And if I search again for a value there, I start at the root. There is only one root. I know where to start. And then I see that the F, I may have more information in another block at a lower level. And finally, after some levels, I can go directly to the block that holds my value. So this is quite efficient to read. The idea of the B tree, the B++ tree, is that the data is only on the leaf nodes, and the internal nodes, the root and the branches, just help to go to the right leaf. And initially, the idea of a B tree was that the same format was used for the branches, the internal nodes, and the values, and it's just those that are read more often that stay in memory, like probably the root will be in memory. But there are some B trees with more optimization when it is in memory. Before that, this is a point query. If I want to do a range query, I need some more information. For example, like we have seen before, a pointer to the next one so that I can just follow to the next one to do my range scan. A lot of B trees use that. But on write, it means that those pointers must be updated. And when you update, you need to lock. There is an alternative. For example, WiredTiger B trees, they do not store links between the leaves to range scan horizontally. They go back to the branches to see the next block, which is more efficient on write because you don't have to update those pointers, less efficient on read, but the optimization on read there is that WiredTiger doesn't really put the offset on files there. It adds real pointers, addresses in memory when the internal nodes are in memory. So more optimization for the branches for the internal nodes and navigation through it to avoid writing too much on the others. Okay, the big problem with B trees is that everything has a place, and this is why it's easy to find. But if everything has a place, an insert must go to a specific block, and when this block is full, then we need to make some room on it, like split it, and the big problem is that we have multiple pointers to update. So you see, for example, that this one is the one that we want to avoid to update in WiredTiger, in traditional B trees. It is updated there. So to go faster on write, because this involves a block split sometimes for some insertion, to go faster, the idea of the LSM tree is that there is not this constraint that a value is at a specific place. Here you see multiple, it's not blocks, it's larger, it's multiple files that are sorted inside them, but they have overlapping values. And it's not only files, there is also one in memory, which means that if I'm looking for a specific value, I need to read from multiple places. So you see how it is less efficient for reads because you need to read from multiple places. But again, this can be optimized. For example, in RocksDB and in many LSM-Trees, you have Bloom filters that can just tell you, oh, this value, no need to look at this file, it's not in this file. There are also, for example, in RocksDB, at least in UGabyteDB, improvements on RocksDB, the minimum value and maximum value of each column is stored so that maybe you can just keep some files, so everything can be faster. But finally, it has to read from multiple places and do a merge of it and a sort merge to preserve the order there. But when you write, it's easier because there is no specific place. You can write where you want. then you choose the faster you write in the memory table that is on top of it. And of course, you allocate a specific size for it. So when it is full, the memory table will be flushed to a file, and you can use, again, another memory table for that. So it's flushed in the background to more files, then it increases the number of files. You don't want to increase the number of files too much, because when you read it, you have to read a lot of files. So there is a background compaction that happens that reads a few files, a few small files, to build a larger file and have less to read. But again, so this is additional work, but again, there are some optimizations. For example, in Postgres, anyway, you have vacuum that has to read data, so this can be offloaded to the compaction. So the compaction is additional work, but can also do some work that the database has to do. Maybe you can gather statistics during that. You can do a lot of things that a database must do in the background. So the compaction runs there to have less files. Okay, so to summarize, when we compare, big difference, the bit tree has a specific place for a value. The LSM tree may have multiple places, so the bit tree is maintained sorted on write, because it is written at a specific place, where the LSM tree is partially maintained sorted because you insert in the memory table and it can be sorted in memory easily, but you need compaction and you need the merge sort when you read it at the end. So this is why we say that B-tree is faster for reads and LSM-trees are faster for writes. But there are many optimizations. B-tree can be efficient on write if a lot of branches are in memory. If you have to follow the 3 or 4 levels of the B-tree and go to disk, that's too much. So usually, B-tree needs memory. LSM-tree, you may allocate less memory for them. B-tree has a space amplification depending on what you write. If you write random values, it will go to random blocks, and then those will be full or split, and then half full. So on average, you have 25% of free space there. But again, you can optimize it. First, all databases that use B-tree have some ways where it can recompact or rebuild the index online. And also on the application, you try to avoid random values like a random UID for a primary key if you don't want to go to the space amplification. Space amplification is not only about the space. It means that it will use also more memory to get things in cache. And for the write amplification that happens when blocks are split, again, there are many optimizations in WiredTiger, for example. There are many optimizations where it doesn't update a leaf in place. It does some kind of copy on write for that. Not having pointers between blocks also allows to avoid locks, so latches, when it reaches the structure. And also LSM-trees have their own optimization. As I mentioned, the read amplification with Bloom filter, min-max. Also, WiredTiger decided to use only one level of the LSM tree to optimize the read and the compaction. Space amplification for LSM tree comes when, for example, when it has to compact, you need double space for it. So for one big database, you don't want to compact all files. But sometimes you need to compact all files because maybe you inserted a very long time ago and you deleted recently. So you inserted a tombstone that is in a different file. But if you do sharding, like Yugabyte or TIDB, they shard before storing in the LSM tree. If you do sharding, you control the size of it, and then the compaction. You can do a full compaction on an amount of data that is limited. For the write amplification, that is low when you write to the memory table, but the compaction needs to keep up with that, because you cannot allocate as many as memory table as you want if it is not flushed and compacted efficiently behind it. But again, there are a lot of things that can be offloaded to the compaction and optimize it. If I compare more specifically, but I think I will go faster on that, the optimizations that were made on WiredTiger B-tree, so I mentioned a few of them. The log3 algorithm is quite nice. It was really built for databases with multiple threads updating data. And also the usage of it. For example, WiredTiger is used in MongoDB. When it generates, it doesn't store directly in the primary key index using the primary key from the application. It generates a sequence that is increasing, so you don't have this space amplification. So the way you use it is also a possibility where it is optimized. And RocksDB and Yugabyte, I already mentioned a few of them, but for example, they support only SSDs because the read amplification, if you add the latency of mechanical disk, can be complicated, but on modern storage that works. And something that is really nice for databases on LSM-Tree, you have incremental backups coming from it because the files, the SSD files, are immutable once they are flushed. So your incremental backup, your snapshot, is just keeping the files. That's quite nice. Something also to keep in mind about the storage. So the mechanical disks used to be slow for everything random, reads and writes. This is why we try to do as much as possible in memory, because the random access is faster, and to do things more sequential when writing to wall or at checkpoint. With SSDs, the reads are faster, so you can accept a bit more read amplification, but the writes can still be slow, so it's something that is optimized by transforming the random writes to sequential writes, because it writes to memory, and then the flush is sequential, the compaction is sequential. So I started with this because I wanted to be sure that I mention it. Write-intensive workload. So with LSM-Tree, the write is faster because you write directly to the mem table, and if all compaction can keep up behind, you write only to the mem table. Where for B-trees, you have to write to the cache, maybe in memory, but you may need to read some blocks, the blocks that you need, the block where the value goes. So additional work. But not all workloads are write intensive. LSM-Trees were really made for big data where you upsert, where you don't have a secondary index, things like Cassandra, for example. But on OLTP, on SQL databases, as I mentioned at the beginning, you read a lot. You need to read a lot even when you insert, which means that with the B-tree, you already have this read done. So this additional thing that you do when you write, you need it to read. Where in LSM-Trees, the read goes to a completely different path and even a different cache. So it is an overhead there. So need to think about it. It's not as easy as I do a lot of writes, I will pick a database with LSM-Trees. Okay? Those are examples of databases using B-trees or LSM-Trees, just to show that it's not only the old databases that use B-trees. For example, AWS has all kinds of databases. Most of them use B-trees. And in the LSM-Trees, of course, you see the big data databases, but you see SQL databases. And so finally, so this is my LinkedIn. If you have any question later, the main message is that, yeah, LSM-Trees are faster for writes, but your database is probably doing more reads than writes, even if you think that your application is writing a lot. LSM-Trees are very complex to tune. There are a lot of parameters to control how the compaction is aggressive or not. So they can be complex to tune, where B-tree may look simpler, but be careful with what you do, be careful with the random keys, for example, and there are different implementations. I was really surprised by WiredTiger implementation because it has a lot of optimizations compared to older databases. It was really made for a time where multiple threads access the same data. And the most important is to understand how it works, understand the trade-off. There is not one that is better than another, but the worst is if you use one without really understanding what happens behind it. Okay, thank you.